Hi, in this video we will derive an improved bar finite element. I've drawn in green the finite element that we derived previously. It's a two-noded element. We have a node at each end. And what we did is we assumed a linear displacement field of the form C0 plus C1x. And then we subjected it to boundary conditions at x equals 0 and x equals L, namely that at x equals 0 the displacement is q1, and at x equals L the displacement is q2. We then substituted that and we solved for C0 and C1. As a result of this linear displacement field, we found that when we took the derivative with respect to x, in other words when we try to look at the strain, we had a constant strain throughout the element. So we'd like to propose an improved bar element, in which case we'll use three nodes. We have an internal node in addition to the two end nodes that we've seen before. And because we have a third node, we have three conditions. We can use a quadratic displacement field. Since we have three constants to solve for, we have three conditions, namely at x equals 0, u equals q1, at x equals L over 2, u equals q2, and at x equals L, u equals q3. It will become a little bit obvious later why I've numbered it in this fashion, although you could name q2 and q3, you could reverse them if you preferred that your middle node was q3. As a result of the quadratic displacement field, we recognize that when we take the derivative of u with respect to x, we're going to get linear strain as opposed to constant strain. Now, why do we think that this should be an improvement? Well, if you recall from the video where we derived the solution for the exact problem, we found that in fact the displacement field was a sinusoidal shape. So it stands to reason that having a more complex displacement field should improve things. Now, instead of, well, let me write this. What we would like to do is we want to write the displacement as follows. This is something we've seen before. That u of x and t is equal to phi x transpose, which is phi of x is the vector of your shape functions. In this case, there'll be three shape functions because you've got three nodes. And that's the dot product of that times q of t. And if I expand that a little bit, this looks like phi 1 of x, phi 2 of x, phi 3 of x, times q1 of t, q2 of t, excuse me, to 3 of t. Well, we'll number this number 1. Let's just number my equations. We'll call this number 2. This number 3, and we'll call this number 4 here. And specifically, if I multiply that out, make it a little bit clearer, this is equal to phi 1 times q1 plus phi 2 times q2 plus phi 3 times q3, where for shorthand I've dropped the x and t dependencies, but that is implied. Now, I want to show you a much easier way to find these shape functions as opposed to the way we did it before when we had to fill in the boundary conditions, substitute the boundary conditions and solve, and then rewrite it in terms of the shape functions and the nodal coordinates. You should hopefully, if you look at this long enough, be able to tell that the nature of the shape functions are such that each shape function is 1 at its own node and 0 at all other nodes. So for example, if we know that the displacement at x equals 0 is q1, then at x equals 0, this must cancel out, and this must cancel out, and phi must just be equal to 1. And a similar case could be made for all the other shape functions. So the shape function is 0 at every other node except its own node, and at its own node it's 1. Oops, I deleted too much here. Just write that again, it's q3. All right, so what we'd like to do is we'd like to find the shape functions, we'll call them phis, by inspection. Once I show you how to do this, you'll probably never opt for the other method again. Alright, so we know that phi1 of x is equal to 0 at x equals L over 2 and at L, and it's equal to 1 at x equals 0. Can you think of a function that would do that? Well, for something to be 0 at a particular point means that it's the root. It has a root there. So if it's got a root at x L over 2, then x minus L over 2 will give a 0 there. And similarly, x minus L will give a 0 at L. So that satisfies the first two conditions. Now, let me change color for this. What happens at x equals 0? Well, at x equals 0, if I substitute 0 into phi1 as it's written right now, I'll get negative L over 2 times negative L, which equals positive L squared over 2. So what do? I simply pre-multiply this by 2 over L squared. Call this equation 5. We'll call this one number 6. And I can do a similar thing for the other two shape functions. So again, by inspection, we'll say that phi2 of x is equal to, just putting in an x will give you a 0 at x equals 0, and we want another root at L. So we go through the same method again of substituting x equals L over 2, and what we get is at x equals L over 2, currently the function will give us L over 2 times minus L over 2, which equals negative L squared over 4. So what do? We pre-multiply by negative 4 over L squared. This will be equation 7. For phi3, can you guess what this might look like? Well, it's 0 at x equals 0, so we put in an x. It's 0 at x equals L over 2, so we put in an x minus L over 2. And again, we play this trick to see what happens at x equals L. Well, at x equals L, we get L times, L over 2, which again gives us an L squared over 2. So I'm going to pre-multiply by 2 over L squared. And just like that, you have your shape functions. Couldn't be easier. I encourage you to go back through it and test it with the different nodal coordinates and see that it works. Okay, so moving on. The next thing we need to do is take the derivative of our shape functions. And this we saw in a previous video, so I'll put a link up here for you to go back to if you've forgotten it. But taking the derivatives of each, and I'm just going to write it out here. You should be able to take derivatives at this stage. But phi1 of x prime is equal to 4x divided by L squared minus 3 over L squared. Excuse me, 3 over L. And we'll call that equation 9. And to try to save space, I'm going to write these all alongside here. Phi2 prime is equal to 8x divided by L squared minus 4 over L. We'll call this equation 10. And then finally, phi3 prime is equal to 4x over L squared minus 1 over L. And what should possibly jump out at you now is the fact that we've taken the derivative and we get a linear function of x as we were expecting, because we described that at the beginning. Now, from the previous video where we derived the 2-node bar element, we found that the element mass matrix could be found as follows. It's rho times the area, assuming that the area of the element is constant. We can bring it outside of the integral. And it's the integral from 0 to L of the shape function phi, or rather this is the vector containing all three shape functions, times phi transpose dx equals, let me write this out longhand just so it's crystal clear, rho a times the integral from 0 to L of, I'm going to drop the x dependency just to keep it compact, but it's phi 1 squared, phi 2, phi 1, phi 3, phi 1, phi 1, phi 2, phi 2 squared, phi 3, phi 2, phi 1, phi 3, phi 2, phi 3, phi 3 squared dx. I remind you that phi 1 times phi 3 is exactly equal to phi 3 times phi 1. We know that this matrix is symmetric. All right. Similarly, for the stiffness matrix, we get K is equal to EA, again assuming that the elasticity and the area remain fixed across the element, or along the length of the element, I should say. And now this is similar, but it's the derivative, phi comma x times phi comma x transpose times dx, which is equal to E times A times the integral from 0 to L. Oh, instead of rewriting it, I'm just going to copy and paste this. Excuse me, that's not how we do it. Okay, and in this case, each of these are primed. Whoops, doesn't work. Prime, 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 prime. And I'm using prime here to denote the derivative, even though back here I said comma x. They're one and the same in this case because phi is only a function of x. Now we know phi 1, phi 2, and phi 3. Those are the equations on the previous page, 6, 7, and 8. We know phi prime 1, phi prime 2, phi prime 3, or phi 3, phi 3 prime. Getting tongue-tied. These are the equations above. So I can now compute this. If I take equations 6, 7, and 8, by the way, this is equation 13, and I substitute that into equation 12, and I integrate, this implies that the mass matrix looks like rho times A times L over 30 times 4, 2, minus 1, 2, 16, 2, minus 1, 2, 4. Equation 14. And we do the similar thing for the stiffness matrix. So we substitute 9, 10, and 11 into 13. And this gives us the element stiffness matrix. Oops. As EA divided by 3L times 7 minus 8 and 1 minus 8, 16 minus 8, 1 minus 8 and 7. And that's equation 15. So just to recap, the way we integrate this matrix, I hope it's not confusing to you, is we actually integrate each element one by one. So we take the phi 1, we square it, and we find the integral of this from 0 to L. You should be able to do this integration yourself, but in general, a very good tool in the future is, if you're not aware of it, is something called Wolfram alpha. so .com. And Wolfram, Stephen Wolfram is the guy that invented Mathematica. And Wolfram Alpha is sort of a watered-down cloud version of Mathematica, but it's great for doing things like symbolic computing. If you have access to something like MATLAB or Maple, those will also work. But I thought I'd just mention it. Now, quick question. What if you were trying to model something where, say, the cross-sectional area was not constant? If you had something like this. Let me just clean it up a bit. What if you were modeling something that looked like this, where A is now equal to A of x? Well, currently we've assumed that A is constant for the element. Can you use this element? Sure, you can absolutely use this element. Your model would look something like this, where each element would perhaps have a different area, but the area on that element is constant. So as you add more and more elements, you're going to get a better and better approximation. On the other hand, if you assumed while you were deriving these elements that A was not constant in each case, you pulled it inside of your integration, or your integral, multiplied that into the mix before integrating, then you're actually going to get an element that's far more suited for this tapered beam problem, or tapered bar, I should say. Why? Because it handles the fact that you don't have constant area. The same way as we've suggested an improvement to the element can be a more complicated displacement field. If you're modeling something that is a more complicated cross-sectional area, then having an element that can accommodate that within the element will make for faster convergence. All right. Now, let's talk about the modeling and assembly of this element. Oops. This is a diagram that we used in the two-noded elements. I've reproduced it here. I've just added a little bit more to it. So the blue would represent modeling this with one element, the axial vibrations of a bar of length capital L. If we modeled it with one element, we would expect two nodes on the outside and one internal node. I've marked it blue just to keep it separate. If we then looked at two elements in the red, we again see that we have an internal node in each case. Same thing for three elements. And then I've gone ahead and done it for n elements. And what you'll see is that with one element there are three nodes, or 3 degrees of freedom. Two elements, there are 5 degrees of freedom. Three elements, there's 7 degrees of freedom. So if I'm going to generalize this to n degrees of freedom, I would say that for n elements, it's 2n plus 1 degrees of freedom. Okay. That should hopefully make sense. We'll use this when it comes to coding it up, but in general, if we're using n elements that have 3 nodes in this case, the total size of the system before we remove the fixed nodes should be 2n plus 1 degrees of freedom. That is the size of the global matrix. A few other things to note is that the length of the element in each case is simply equal to capital L, the length of the bar, divided by n, the number of elements. We can call that 16. So if I substitute that into my mass matrix, I find the following. I find that I can rewrite my mass matrix as rho times A times L divided by 30 times n. And this again is 4, 2, 1, 2, 16, 2, minus 1, 2, and 4. And I'm going to use the exact same treatment as we did for the two-noded element, where because we don't have the geometric and material properties, we're going to lump this into a constant we call C1, Cm. and write it as follows. 4, 2, 1, 2, 16, 2, minus 1, 2, 4. And that's it. 17. Similarly for K, the element stiffness matrix is equal to EA divided by 3 times N over L times 7 minus 8, 1 minus 8, 16 minus 8, 1 minus 8, 7. And again, like we did in the previous case, we'll call that CK times N over 3 times, again, 7 minus 8 and 1 minus 8, 16 and minus 8, and 1 minus 8 and 7. Call that 18. And I'll just put here for good measure that Cm we defined as rho times A times L. Call that 19. We define Ck as E times A divided by L. That's 20. And I remind you that A is equal to the square root of Ck over Cm, which can be rewritten as 1 over L times root E over rho. And let me remind you that for the purpose of solving this, what we can do is we can set Ck and Cm in this case equal to 1. And whatever result we get for the frequency, we can just multiply it by A. I'll put a link here to the video, to the previous video where we went through all of this. There's no need to reproduce it here again. And there you have it. So these are the stiffness and mass matrices for what we believe to be an improved finite element, a bar element. Why is it improved? Well, because we've added an extra node, and in doing so, that has allowed us to assume a quadratic displacement field instead of a linear one, like we did with the two-noded element. And we believe this is an improvement because we know from the exact solution that actually the displacement field is sinusoidal in nature. So thank you for watching this video. I hope it proved to be useful to you. If it did, please give it a thumbs up so that others can get to watch it. And we'll catch up with you in the next video when we'll enhance our previously coded Python code to include the three-noded element. Thank you for watching.